G'day everyone. Today we're going to be learning about how to sum an arithmetic series or an AP. I'll be walking you through the equations on how to sum these series, as well as taking a look at a few examples. Now in this orange square, we have two formulas for the sum of an AP, or an arithmetic progression, or an arithmetic series. What I'm going to do down below is just work out how we actually calculate that and how we get these equations. So how do we define an arithmetic progression? Well, this is where we have a common difference D and a starting term A. So if we consider a series with, let's just say, n terms, we can say we have A plus D, which would be the second term. The third term would be A plus 2D, A plus 3D, and this would go on until we eventually finish, and we would have A plus ND. Sorry, not that. We would have A plus N minus 1D. Now there is another way that we can write this, and instead of A, let's consider the last term L. And we can say, well, this will be L minus 3D, L minus 2D, L minus D, and L. So we have this series that starts at A and ends at L, and we progressively build up, and we keep building up, except, we can write it in a different way, phrasing it in terms of the last term instead of phrasing it in terms of the first term A. So now that we observe we can write it in this sort of way, what happens when we want to sum all these terms? So what I'm going to calculate is Sn, which is the sum of n terms. So let's say L is the nth term. So if it's S100, L is going to be the 100th term. And so the sum is going to just look like A plus D plus A plus 2D plus all the way up to, and let's go L minus 2D plus L minus D plus L. Now, I'm going to write some brackets around these terms here just to make it clear as to what I'm going to do next. So let's call this equation 1, and let's write the series again, except let's write it the other way around, starting with the last term, because we can essentially flip this around and it will be the same thing, in the sense that 1 plus 2 plus 3 is the same as 3 plus 2 plus 1. We can flip it around, but they're both still going to equal the same thing. So when we write it the other way around, we have L plus L minus D plus L minus 2D plus all the way up to A plus 2D plus A plus D plus A. Now let's call this equation 2. Now, if we were to add these two equations, on the left-hand side, we're adding 2 SNs, so we will have 2 times SN. And when we add 1 plus 2, what we can see is that here we will have A plus L. Over here, we will also have A plus L. And that is because we have the A, we have the L, and then the D's sort of cancel out. We have a plus D and a minus D. Now in our next term, what we see is that we have, again, it will be A plus L. And this is because we have a 2D and then a minus 2D, and they will cancel each other out. And then that leaves us with A plus L. And we can keep going, and you guessed it, you can do the same thing, but you'll keep getting A plus L's. So how many is this? Well, this is actually just n lots of A plus L, because we have n terms. So this is our first term, our second term, our third term, so on. And then our last term will be our nth term. So when we sum all of these together, we will have n lots of the same term. So we will have n lots of A plus L, which is what this is. And if we wanted to make Sn the subject, the sum of the nth term, well, this is just equal to half n outside of a plus L. Now we know L is the last term, and for Sn, this will be the nth term. So SL will be the nth term, which we should know is a plus n minus 1 d. And so if we substitute L for, if we substitute this for this, because we know that this is equal to L, then what we also get is that Sn is equal to is equal to half n outside of a plus our L, which is a plus n minus 1 d, which is just equal to half n outside of 2a plus n minus 1 d. And we can see that this is equal to the two formulas that we have up here. And so this is our first formula that we had, and this was our second formula. So this is 1 and this is 2. So the use cases for both, so when we would use this is when they give us the first and the last term as well as the number of terms. This is the equation that we would prefer to use because obviously it looks a lot easier than using something like this. However, sometimes they don't always give us the last term. So if that's the case, we will need to be using this formula because obviously we can see that it doesn't rely on the last term. So now that we understand how to develop these equations, let's actually put this into practice and use these two formulas to answer a few questions. So in our first example here, part A says find how many terms are in the sum 41 plus 45 plus 49 all the way until 401. So we know A is equal to 41. We can see that D is equal to 45 minus 41, which is equal to 4. So that's our common difference. And with this, we know that Tn is equal to A plus n minus 1d. This is the formula for the nth term. So if we plug in our last term, which is 401, we'll be able to figure out how many terms are in the sum. So 401 is equal to 41, which is A, plus n minus 1. So n is what we're going to be solving because the value for n will be our last term, times 4. And this is equal to 401 equals 41 plus 4n minus 4. We'll have 401 equals 37 plus 4n. 401 minus 37 is equal to 364. So we have 364 equals 4n. And if we divide this by 4, we get 91. So therefore, there are 91 terms in the sum. So that's part A. Now part B says hence evaluate the sum, and it just sort of rewrites that sum. So we know that we can use two formulas. It could be half n outside of a plus L, or it could be half n outside of 2a plus n minus 1d. Now which one are we going to use? We can actually use both because we know what the number of terms are, we know the difference, we know A, but we also know the last term. And so if we know the last term as well as the first term and the number of terms, it's just always easier to go with this equation because it's just nice and simple. So we should know that the sum of these 91 terms, our Sn, is equal to half times 91 times outside of our first term, which is 41, plus our last term, which is 401. And if we plug all of this into a calculator, we get 20,111, and that's our answer. In our next example, part A says find an expression for the sum Sn of n terms of the series 40 plus 37 plus 34, and so on. So we should recognize that this series is an AP with a first term of 40 and a common difference of 37 minus 40, which is minus 3. And we know that Sn, the sum of n terms, is equal to half n outside of 2a plus n minus 1d. We also know that there is another formula, half n outside of a plus l, but we aren't going to be using this. We aren't going to use this for this question because this is an ongoing series and they don't necessarily define the number of terms. So we don't really know what the last term is for any given question. So that's why we are going to be using this formula for this question instead, because we don't know what the last term is and we don't rely on it when using this equation. So now we can plug in all our terms and we can say the sum Sn of n terms of this series is half n outside of 2a, which is 2 times 40, plus n minus 1d, which is times minus 3. And what we can do is we can sort of just simplify all this. And we can keep going. And keep going. And I think we'll just leave it there. And that's going to be Sn. So then part B says, hence find the least value of n for which the partial sum Sn is negative. So all this is saying is at what term is the sum negative? So we can see that we have 40 plus 37 plus 34 plus and so on. And what we'll eventually get, because this is a decreasing series, is we'll eventually hit some negative numbers. And when we do hit negative numbers, eventually at some point, the sum of this series will turn negative. And the question is asking, well, at what point do we turn negative? After how many terms will this sum be negative? And this is just when Sn is less than 0, and we're going to be solving for n. So if we plug in our equation, we have half n outside of 83 minus 3n is less than 0. So this is nice and factorized, so we'll actually get half n is less than 0, or 83 minus 3n is less than 0. Now this results in n is less than 0, but this has no solutions. Now why does it have no solutions? Well, n itself can't be negative because n describes the number of terms. You can't have a negative number of terms. If I was to ask you what is the negative second term, that doesn't really make sense because you can only really start at your first term and go onwards. You can't have negative terms. So that means our solutions are going to be coming from this equation. And when we solve it, we have 83 is less than 3n. And then if we divide 83 by 3, we will get that 27.666, so on, is less than n. Or I'll just rewrite it as n is greater than 27.66 recurring. So what is our term n for which this sum is first negative? And that will be 28. It'll be the 28th term. Now why isn't it 27? Well, this is, if the answer was 27, it wouldn't satisfy this inequality because 27, which we're saying is n, is not greater than 27.66. So we are looking for the first term, and it needs to be a whole number, because remember we need whole numbers as terms. N can only be a whole number. The first whole number that satisfies this inequality, and so the first whole number where n is greater than 27.66 is when n is equal to 28. Hope that makes sense. And that is how we solve this question. So the last example we're going to take a look at says the sum of the first 10 terms of an AP is 0, and the sum of the first and second terms is 24. Find the first 3 terms. So what we're going to do is we are going to break down this information. So the first bit of information says the sum of the first 10 terms of an AP is 0. So S10 is equal to 0. Now we should know that S10 is equal to half times n, which is 10, outside of 2a plus n minus 1, which is 10 minus 1, d. Now this is all equal to 0, so let's say it's half times 10, 2a plus 10 minus 1, d, and this is equal to 0. Let's simplify it and say 2a plus 9d is equal to 0. 2a plus 9d is equal to 0. And this is going to be our first equation here. Our second equation is going to come from the second bit of information, which is the sum of the first and second terms is 24. Now we don't actually need to do a fancy, like use the proper equation, because it just says the sum of the first and the second terms is 24. We can just say, well, the first term is a, and the second term is a plus d, and that's equal to 24. So I have 2a plus d is equal to 24. Now I'm just going to rewrite this to make d the subject, and that will be our second equation. So if we sub 2 into our first equation, so we're subbing d equals 24 minus 2a for d over in equation 1, we get 2a plus 9 outside of 24 minus 2a, and that is equal to 0. We get 2a plus 9 times 24 is 216, minus 18a is equal to 0, minus 16a is equal to, plus 216 is equal to 0, and we get 16a is equal to 216. So that means we get a is equal to 13.5. Now, what is our common difference? Well, if we substitute it into here, we say therefore d is equal to 24 minus 2 times 13.5, and that is equal to -3. So now that we know our a and we know our d, we can figure out the first three terms. So t1 is equal to 13.5 because that's equal to a. T2 is equal to 13.5 minus 3 because it's our first term minus plus the difference, which is -3. And that equals 10.5. And our third term is 10.5, which is that second term, minus 3. And that gets us 7.5. And that's our answer to this question. So I hope that made sense. To recap, in this lesson we looked at summing arithmetic series, and we looked at the equations, the two possible equations that we can use to sum arithmetic sequences and series. And we also just looked through 3 different examples on applying those formulae. Hope that helped. If you have any questions, please leave a comment and I'll be sure to answer properly. See ya.